Hello everyone, welcome to the lecture 57 of the course Diffusion in Solids. So, last couple of weeks we have been talking about some salient features of diffusion in different classes of materials, and today we will start with the last category of the material that we are going to take, which is the ionic solids. Now, ionic solids, as the name suggests, they have the ions which make the crystal, and of course, the bonding that exists is ionic bonding. So, that is why because of now the constraints of the charge neutrality, the bonding is different, and therefore, the way in which the atoms move are different. In addition, the conductivity and the diffusivity also gets coupled, because the ions are also responsible for conductivity. So, there are a lot of things that are slightly different in the case of ionic solids. So, we will be covering their diffusion aspects in two lectures. So, today we will talk about the point defects in ionic solids, although we introduced slightly when we were talking about the structure and defects in solids. But today we will go in more detail about these defects, and then we will take an example of diffusion in silver halides today, and what is the effect of doping. So, these are the keywords. So, we have seen that ionic crystals are characterized typically by two sublattices, a sublattice of cations and a sublattice of anions. And because of the Coulombic interactions between the ions, the structure is completely ordered. And the diffusion of a given ion is restricted to its own sublattice, because if it moves to another sublattice, it will face huge electrostatic repulsions, or huge electrostatic forces rather, which will then disturb the whole crystal. So, therefore, the diffusion of a given ion is restricted to its own sublattice. So, here are some common examples. For example, this is a calcium fluoride structure where you can see each calcium is surrounded by 8 fluorine atoms. Each fluorine atom is surrounded by 4 calcium ions. You have a CsCl, which is a B2 kind of a structure, where corner atoms are chlorine ions, whereas the body centered is cesium. You have NaCl structure here. So, the corner atoms are all the chlorine atoms. The sodium atom is surrounded by 6 chlorine. Similarly, each chlorine is surrounded by 6 sodium atoms. Now, we saw already a little bit about the defects in ionic crystals. Now, here this picture actually summarizes some important point defects that occur in ionic crystals. So, this is a two-dimensional array. The plus and minus represents this is a cation, this is an anion. So, cation, anion, cation, anion, like that. This is a two-dimensional sublattice. Now, you see that, for example, when you have a case where this should have been a minus here. So, minus plus minus, but this is vacant. So, anion vacancy plus here a cation vacancy. So, when an anion and cation vacancy exist together, this is known as what we call as a Schottky defect. Here the cation has moved to the interstitial site. So, this constitutes what is known as a Frenkel defect. Then you have let us say this is you can see this is a circle in which two plus signs are present. This means it is a impurity which is a divalent impurity. So, it is a divalent cation impurity, and when it is present together with the vacancy, we call it as a impurity vacancy complex. Then if the reason is that because whenever now the divalent cation is added, extra charge is being added. So, therefore, a cation vacancy has to be created in order for the charge to be neutralized. And here also remember that when a cation is missing, that means a vacancy of a cation will carry a negative charge, and a vacancy of anion will carry a positive charge. So, this is again from the constraints of the charge neutrality. And you can also have, so in this case here what is illustrated is that they are together, they form a complex, but they can also exist separately. We will see that whether they form complex or not, it depends upon certain factors like temperature and so on, and the concentration of the divalent ion as well. Then it is also possible that a vacancy pair exists. So, for example, here this is a anion vacancy, this is a cation vacancy. So, as I said that the anion and the cation vacancies are of the opposite charges. So, sometimes they do come together and form a vacancy pair. The pair as such is a neutral in nature because it has both plus and minus. So, these are some of the important defects, and we will see a little bit more about them in the coming slides. So, what we classify the defects in ionic crystals are in two broad categories, which are intrinsic defect and which are extrinsic defect. So, intrinsic means that even in a ionic solid where no doping is carried out or no additional element is present, even in such a pure ionic solid, the defects that are present are known as intrinsic defects. So, the one example is the Schottky disorder, so or the Schottky defect. We had seen this equation before when we talked about the defects in crystalline solids. I have just summarized the equation here, that the concentration of vacancy of cations, so a concentration of the cation vacancy CVC means the concentration of the cation vacancy. Vc represents the cation vacancy, Va represents the anion vacancy. So, capital C Va means the concentration of anion vacancy, capital C Vc means the concentration of cation vacancy. Their product is equal to exponential minus GSP by KBT, which is equal to KSP, which is a function of temperature. So, this KSP is known as the Schottky product. And the GSP, what is written is it's a Gibbs free energy for the formation of a Schottky pair. So, this KSP is what is an equilibrium product. So, we will see that this is an equilibrium defect, and the product, the charge neutrality demands that this product is constant. We will see cases where due to impurity addition, one of the CVC or CVA may rise, but then the other has to decrease to maintain this product constant to maintain the equilibrium conditions. So, you may also have another intrinsic defect which is known as the Frankel defect. So, Frankel defect as we saw in the previous slide means that cation vacancy exists and the missing cation occupies a interstitial position. So, the CIC here represents the concentration of the cation interstitials, and CVC is the concentration of the cation vacancy. The product of these two again is written as exponential minus GFP by KBT, which is equal to KFP, which is called as a Frankel product. Now, this Frankel product is also dependent on the temperature, and like this Schottky defect, we also have the equilibrium KFP, that is the Frankel product. And GFP is a Gibbs free energy for the formation of the Frankel pair. So, here are some examples of the dominant disorder which exists in different types of ionic crystals. For example, in alkali halides which have NaCl type of structure, Schottky disorder is prevalent. In alkaline earth oxides also Schottky is present. In the silver halides, which we will be talking about today, although they have a NaCl structure also, but they have there the dominant defect is the cationic Frankel defect. Then Schottky defect is also present in CSCl type of compounds, or BeO, MgO, etc. Then anionic Frankel is present in alkaline earth fluorides, thorium oxide, which crystallizes in the calcium fluoride structure. So, in the undoped crystals with the Schottky disorder, so that means if there is no external impurities are present or the crystal is undoped, then we can say that CVC 0. So, 0 means intrinsic defect. So, CVC 0 is equal to CVA 0 to maintain the charge neutrality. that is equal to exponential Sp by 2 kb into exponential minus hsp by 2 kbt. This is essentially breaking the free energy as H minus Ts. So, this then becomes equal to root Ksp, where Ksp is a function of temperature. Similarly, in undoped crystals with Frankel defect, you will have CVC 0 is equal to CIC 0. Again, this is the product containing one entropy term, another enthalpy term, and this is equal to root Kfp T. If the formation enthalpy for the Schottky pair and Frankel pair are similar, then both can exist, and based on the charge neutrality condition, the CVC can be written as CVA plus CIC, provided all ions have the same charge. Heterovalent doping that requires creation of additional cation or anion vacancies. So, when you add heterovalent impurities, then additional vacancies will be created. The third type of intrinsic defect is what is known as the vacancy pair. That means, if the cation and anion vacancies which bear opposite charges, they can attract each other by the Coulombic forces. So, this is written as Vc minus plus Va plus equal to Vp, which is the neutral defect. So, the concentration of such pairs can be written as Cvc into Cva into Zp exponential delta Gp by kBt, where Zp is the number of distinct orientations of the pair. In NaCl, for example, Zp is equal to 6. Again, one can write this delta Gp as GSP, that is the Schottky product minus delta Gp divided by kBt. So, here the delta Gp is the Gibbs free energy released when two isolated vacancies form a pair. So, as I had indicated before, that vacancy pairs are neutral, therefore, their motion does not contribute to the ionic conduction, but they do contribute to the diffusion. So, because they do not carry any charge, so they do not make any contributions to the ionic conductivity, but they definitely contribute to the diffusion phenomena. Then we talk about what are known as extrinsic defects. That means, when you add dopants, so the additional defects are created when aliovalent dopants are added. Aliovalent means that whose valency is different from the valency of the ions present in the ionic crystal. For example, if Ca2 plus is added to NaCl, a cation vacancy must be created in order to maintain the charge neutrality. And depending on the temperature, the cation vacancy can be isolated or associated with the impurity. So, there are two things. One, when you add ion which is has a different valency than the constituents of the ionic crystal, then the additional vacancy must be created. So, here Ca2 plus is added to NaCl, so a cation vacancy is created. The second thing is whether this created vacancy exists alone, or it forms a complex with this added ion. So, this depends upon the temperature, and if the temperature is low enough, then the impurity vacancy complexes can form. So, these form at low temperatures. If a divalent impurity is added, then I plus Vc minus gives IVC. Vc minus is basically referring to the cation vacancy, which carries a negative charge. Now, this concentration of this free vacancy is equal to Ci minus CIVC. That means, certain vacancy would form the complexes. The remaining, when you subtract from Ci, will lead to the concentration of the free vacancies. If you take Ci out, then Ci is equal to 1 minus CIVC by Ci, which is written as P. So, P, as you can see, it is called as the degree of association. It is equal to the number of ion vacancy, the impurity vacancy complexes divided by the concentration of the impurity. In fact, one can also write an expression like P divided by 1 minus P whole square is equal to Ci into ZIVC exponential delta GIVC by kBt, where delta G I we see is the Gibbs energy of association, and Z I we see is the number of distinct orientations of the complexes. Now, let us go through some of the features of the conductivity and the diffusion in silver halides, AgCl and AgBr. So, here is the structure, as I said that it is similar to the NaCl structure. Now, these halides find important applications in the photographic process actually. The ionic conductivity of these silver halides is several orders of magnitude higher than the alkali halides, which are NaCl and KCl and so on. The predominant defects in these silver halides are the cation Frankel defects, that is Ag vacancies and the interstitial Ag plus ions. Okay. So, in the alkali halides is a Schottky defect, but in the silver halides it is a Frankel defect, and that too cation Frankel defects. The interstitial Ag plus ions are more mobile than the Ag vacancies. So, remember this, that now when we are talking about the Frankel defect, there are two defects actually. One is the Ag vacancies, and now the silver ion has moved to the interstitial. So, there is a interstitial Ag plus ions. So, these interstitial Ag plus ions are actually more mobile than the Ag vacancies, and therefore, the ionic conductivity is mainly due to the contribution of Ag plus interstitials. Vacancies make a minor contribution. And similarly, the self diffusion of silver is also predominantly due to the Ag plus interstitials, and to further very less extent due to the Ag vacancies. So, the self diffusion studies reveal that the anion diffusivity is 3 to 4 times 3 to 4 orders of magnitude in fact lower than that of Ag plus ions in both AgCl and AgBr. So, Br and Cl both diffuse much slower than the silver ions, and the anion diffusivity is mediated by the anion vacancy, as I had told before that it is the case. Their number is small and they are part of the Schottky pairs. In the intrinsic region, the dominant diffusion mechanism of Ag is the interstitial C mechanism, and several types of jumps, collinear and non-collinear ones contribute to the Ag diffusion. Okay. So, here you can see this is the interstitial C mechanism, and here is an example of the collinear jump. That means this ion, silver ion, is pushing out another ion from its position. This will move to interstitial, this will occupy its position, and this is happening in a collinear way. If it goes in this direction, this direction, this direction, this is a non-linear or non-collinear motion. The migration enthalpy for Ag plus interstitials for collinear and non-collinear jumps is very low, like 0.04 to 0.1 electron volt, and that is possibly due to the quadrupole formation in Ag plus ions along the 110 direction. The diffusivity of both cations and anions exhibit what are known as intrinsic regions and extrinsic regions, and at low temperatures the diffusion of silver takes place via the extrinsic vacancies. We will see shortly in the ionic solids, typically when you have a diffusion versus temperature plot, you can see the intrinsic as well as the extrinsic regions reflected there. So, the diffusion coefficient of silver, the tracer diffusion coefficient of silver can be written as FV A square omega VAG into C VAG, very similar to what we had seen earlier for metals and metallic alloys. The vacancy mechanism, this is the contribution of the vacancy mechanism, plus because in the silver halides both are present. So, there is a vacancy as well as there is a interstitial. So, the interstitial C mechanism also can contribute to diffusion, and hence while writing the tracer we need to write both. So, this is written as summation I either collinear, non-collinear, Fi into Gi A square omega IAG CIAG, where we know A is the lattice parameter, omega is the jump frequency, F is the correlation factor, and CVAG or CIAG are the concentrations. Now, if the mechanism is direct interstitial or the mechanism can be indirect interstitial. So, direct interstitial is what is illustrated here. So, this interstitial Ag plus moves to another interstitial site. This is called as a direct interstitial. Indirect interstitial means this Ag plus ion will push another Ag plus ion. This Ag plus ion will get into the interstitial, but the original Ag plus ion occupies this position. So, this is known as a knock-on process. This can be collinear or non-collinear. So, the Haven's ratio, which is the ratio of tracer diffusivity to the charge diffusivity, is written as d star Ag by kBt into sigma dc divided by NIN into q square, where NIN represents the number of ions, sigma dc is the charge diffusion coefficient. This HR contains also the factors of various correlation factors of various mechanisms. Then what happens when you dope these silver halides? So, doping with divalent cations like cadmium 2 plus, that increases the number of vacancies. As we saw, to maintain the charge neutrality, if you add a cation, then it will lead to the additional vacancies. However, as the Frankel product should remain constant, so the Ag plus interstitial concentration decreases with increasing CD2 plus concentration. So, as you increase more and more CD2 plus, Ag plus interstitial concentration will come down. As a result, in the intrinsic region, the conductivity is independent of the concentration, but in the extrinsic region, the conductivity decreases with increasing doping until a minimum is reached. So, you can see this is how the variation looks like with sigma versus 1 by T. This is the intrinsic region, this is extrinsic region 1, and there is another extrinsic region 2. So, we will see that as you go on increasing the temperature, you enter the sigma, you enter the extrinsic region, and the sigma decreases with increasing doping until a minimum is reached. At this, so it will become more clear with this figure. So, for example, this is drawn at a particular temperature. So, you see that initially when the divalent cation concentration is small, it behaves like a intrinsic solid. After a certain concentration, then there is a dip in the curve because the conductivity starts decreasing with increasing doping concentration. After the minimum, what happens? So, at the minima, actually there are two things. So, as you add more and more dopant, the concentration of vacancies is increasing, and the concentration of interstitial is coming down to maintain the product. However, we have earlier pointed out that the interstitial ions are more mobile. So, what happens at the minima? There is a two opposing things become equal. That means, the contribution due to vacancies is equal to the contribution due to Ag plus interstitials. So, vacancies are more in number, but they are less mobile. Similarly, Ag plus interstitials are less in number, but they are more mobile. So, as if you are at a lower temperature, this minima also shifts to lower divalent cation concentration. In the extrinsic region too, as I already said that as doping increases further, Ag vacancies dominates and the conductivity starts increasing. So, as now more and more doping increases, then the vacancies become more and they start contributing to the ionic conductivity. At higher temperatures, interactions between defects become more important and causes upward curvature in the slope. At lower temperatures, as we have seen before, the complexes between oleovalent impurities and vacancies form, resulting in the downward curvature in the extrinsic region. So, here are some of the examples. Some numbers are given for formation enthalpy of Frankel pair 1.24 to 1.44 eV. For AgBr, it is slightly lower. Then this is a migration enthalpy of the cationic vacancy. This is a migration enthalpy of the Ag plus interstitial. So, you can see that the migration enthalpy of Ag plus interstitial is much lower than the migration enthalpy of the cationic vacancy. So, therefore, the predominant mechanism is, or one of the important mechanism is the diffusion through the interstitial C mechanism in the silver halides. So, with this we will end our discussion for this lecture, and we will continue talking about diffusion in ionic solids by taking examples of alkali halides in the next video. Thank you.